In this brief lecture, we're going to talk about the full scope of mathematics, at least in a broad brush sort of style. Uh, we're not going to talk about any particular historical events, though we will talk about how the course will progress. The general topics of mathematics in this course include number, ordinal versus cardinal, and base. For example, binary, ternary, decimal, and so on. These were taken up in the previous lecture. But coming ahead is the arithmetic, which is addition and multiplication, and the very important fractions. Geometry, which includes area and volumes, and the very important concept of similarity. Number theory, various assertions, theorems, and facts about numbers themselves. For example, the Pythagorean triple, 3 squared plus 4 squared equals 5 squared. Prime numbers, perfect numbers, and many, many other kinds of numbers. Algebra, mostly on the solution of equations, but also on the nature of the solution of equations. And not mentioned here, but coming much later in the game, are things like calculus and analysis, graph theory, abstract algebra, logic, and so forth. With number and base, we talk about the number and types of symbols. We talk about a positional versus non-positional representation of numbers, and what are the advantages or disadvantages of each. Positive numbers and negative numbers form an important component of early mathematics, noting that some ancient mathematicians would not accept negative numbers either as solutions of equations or as entities in and of themselves. The very important topic of fractions seems to be a topic that causes difficulty even today with school children and adults, but it also caused serious issues in the ancient world. With fractions, then we come up to rational numbers, which are the ratios of whole numbers. And then beyond that, we get into incommensurable numbers, those that basically are not rational. They have quite a history of themselves. The square root of 2 you recognize as an incommensurable number, as it cannot be expressed as the ratio of two whole numbers. The basic operations of arithmetic are considered in the following lectures. There's the binary based, there's table based, and then there's the idea of grouping of symbols to produce numbers and to do arithmetic. Then we'll discuss algorithms for multiplication and division and how they have evolved over the last 2 millennia. We'll talk about the nature of fractions and their companion decimals, which came along much later, remarkably. And then we'll talk about taking square roots and finding these so-called incommensurables and all the other kinds of numbers that are scattered about. In geometry, we'll talk about the ideas of similarity of figures, which is a really important concept. Similarity is at the foundation of geometry. We'll talk about formulas for areas and volumes, and also some of the formulas that were incorrect but used. it makes one think that maybe we currently have incorrect formulas. And we do. Anyone who thinks pi is equal to 22 over 7 is using an incorrect value for pi, but it works uh, in limited circumstances. We'll talk about the classification of curves and shapes. So, for example, there's the conic sections, parabola, hyperbola, ellipse, and circle. But there are many other shapes, such as a crescent shape, which is also known as a lune in antiquity. We'll talk about regular solids, such as a cube and others. Then we'll talk about the full axiomatic development of geometry, which came long after most of geometry was already well understood. And with that, in geometry would come the method of exhaustion, which was basically the first limit. Number theory is a very important topic even today. It forms the theory of number theory forms the basis of almost all modern cryptography schemes. But that didn't start that way. We'll have figure-it numbers such as 1, 3. What comes after 1, 3, 7, and so on. Numbers. There's the Pythagorean triples, of which I just cited one, 3, 4, 5. There's 1, 5, 12, 13, where the sum of the squares of 2 is equal to the square of the third. There's also a so-called Pythagorean quadruple, which you might look up online. There's a characterization of numbers into primes, amicable, abundant, deficient, and that all depends on the types of divisors they have and how many there are. There'll be theorems about numbers and tables of results. There's rational numbers and incommensurable numbers. For example, the square root 2 took many centuries to assimilate through its geometric origins. In algebra, it began with the solution of equations, notably linear equations, and that was easy. It can be done easily in a geometric way. And then quadratic equations, and we'll see that the ancients distinguished many different kinds of quadratic equations and their form, because often they would not allow negatives and negative solutions, which is also an important topic. And it took millennia to accept negative solutions. And of course, culminating all of this is the solution of linear systems, where you have more than one unknown. Other aspects of mathematics include the level of rigor, from examples to formulas to theorems. The level of rigor is a foundational topic in many subjects today that are trying to emulate the mathematical model. The mathematical model and rigor we have today took a long time to evolve. We'll talk about dynamically and statically defined curves, and we'll talk about rhetorical versus symbolic expressions. Remarkably, most mathematics was rhetorical in its early days, and only later did it become symbolic as we understand it and use it today. We'll talk somewhat about applied mathematics and pure mathematics and what's the difference between them. And the difference is narrowing, you might say, that the one impinges the other more and more. Pure mathematics often feeds off of physics and applied topics. Uh, uh, when mathemat when mathematicians are left on their own, they produce sometimes they produce theories that have very little value but extreme depth. We'll talk about angular measurements. These are important in astronomy, which is one of the early topics that civilizations considered, even some claiming dating back 15,000 years ago. And we'll talk about the quadrature of shapes. This is basically finding the area of various shapes, and this generated a need for limiting like processes, which is the foundation in calculus. So that's what we're going to do. And we'll look at problem solving by example, by the method of false position, where you put in a false solution and determine how to make it, and determine how to correct it. We'll talk about geometric construction, and we'll talk about the use of rhyme in problem solving. In fact, the original solution for finding the roots of a cubic was expressed as a rhyme. Rhymes are very powerful in remembering. Well, these are the topics. They'll be considered as contributions from the ancient and modern epochs, from civilization to civilization, and then more recently in the last several hundred years from country to country. Hope you enjoy.